Today's episode was made possible through the continuing support of Gina Higdon. Thank you, love. Hi there guys, welcome back to the shop. Today as we do a deep dive into the world of microwave oven transformers, and we're going to cover a little bit of the basics of how transformers work. It all basically stems from about 100 years ago. A whole lot of very smart, curious people just like you spent a lot of time farting around with iron cores and bits of magnet wire. They didn't even have magnet wire back then. They were just using regular wire with whatever kind of insulation they could figure out. This is the basis for so many things. Nothing more than various arrangements of wire and steel, and putting these together in different ways and farting around with magnetic fields. Everything in this whole genre is the manipulation of alternating currents and magnetic fields. So let's take our standard microwave oven transformer, and this is fresh. There's nothing special about this. I haven't modified this in any way because I wanted to start with something that you're going to intrinsically understand, because it's the same thing that you have sitting on your bench right now. So let's look at what we've actually got. So as we look at the side of a standard microwave oven transformer, we can learn really quick there's 4 main parts to this, and that's it. It's a really simple device. We have our big outer core. This is called an EI core, and we're going to get into why it's called an EI core in a bit. There are different types. There's like I, C, E cores, all kinds of stuff, but this is an EI core. We have our primary winding down here. This is the large amount of big fat wires. That's your primary. The primary winding on a transformer is the winding that you put electricity in on most of the time. Some transformers we use backwards, so they'll be labeled with the primary as what we're actually using as a secondary. But this is your primary winding. This is where we put electricity in. So we apply 120 volts wall power to this. The second winding you're going to come across is this little one right here, this extra wire hanging out. That's actually a winding. This is called the filament winding. This winding on this transformer is used to power the filament inside the magnetron. We don't actually use the filament winding, but for this transformer, the filament winding is putting out a very, very low voltage, so there's only going to be a few turns at a pretty tiny current respectively, so it's not very thick wire. But the little thing in the middle, this extra oddball wire hanging out, is the filament winding. The next winding we come across up top here, this is the secondary winding. This is where we get the high voltage out. On microwave oven transformers, it's usually grounded at one end to the core, and the other end is a single high voltage terminal. Some high voltage transformers like MOTS, it's rare with MOTS, but sometimes you'll get a MOT where both ends of the high voltage are brought out to wires, but usually one's grounded to the case. So let's take a minute and dig inside a microwave oven transformer and figure out what parts are what. All right, so we start out here with the core. The core is not a single piece of steel. It's actually thousands of them. Each one of these lines is a separate steel plate. They're coated in shellac, they're welded together, but the idea is instead of using a single monolithic block of steel, which you can do, it just works a lot better to have a whole bunch of little tiny ones laminated together. This is because of the way the magnetic fields work and the eddy currents that are induced in the core. It's a lot more efficient to have a whole lot more little tiny stamp pieces than to have one big piece. It's also a lot easier to make, because if they wanted to make a solid core like this, you'd have to machine out big chunks of steel. Instead, what they do is they just stamp these off out of a big sheet. Well, usually it's a long ribbon. There's chunk, 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 and they stamp them all out. Then they stack them up, and you can get big, thick, chunky shapes out of really thin, cheap steel. And everything involving microwaves is all about being as cheap as you possibly can. So we call this kind of core an EI core, and I'm going to show you why. Because the shapes of the two different pieces in the core are E's and I's. and then they get attached together as they get laminated. So it's an EI core. This is absolutely one of the 3 most common types of transformer cores you're going to find, and you'll find them in sizes from like this big, the size of a quarter for little PCB mount transformers, up to 100 kVA pole pigs. You'll find EI cores used everywhere. It's absolutely probably the most common type of transformer. Another thing we notice on this particular core, we can see the rivet and attachment point for what was the high voltage winding. One end of the high voltage winding attached here to the core and was just grounded out. So as we saw before, we've got our big windings on the bottom, our filament winding in the middle, and our secondary winding up here with the tiny wire. So let's take a look inside and see how these work. So here I've got our winding burger. This shows us the arrangement of the windings. I've cut them all off nice and clean. That took doing. But we've got them all cut off nice and clean here, and you can really get an idea of what we're dealing with. For the primary winding, we don't have a lot of turns, like comparatively, but it's big chunky wire. That's probably about a 12 gauge wire there. Then there's our filament winding, which is only 3 turns, which is funny because it's probably only giving us about 3 volts. So our filament winding is a really tiny wire with a lot of insulation, so it's going to be working at, in a high voltage environment, but it's a tiny little wire inside, and there's only 3 turns. And then our secondary winding up here is a lot of turns of crazy tiny wire. Look at how tiny that is. And this is all machine wound, so it's all like neatly arranged and just perfect. But that gives you an idea that we have a whole lot of voltage up here. So we start at a low voltage. We're pulling off as one of our, well, we could call that a tertiary winding, but I like to think of it as just 2 secondary windings. So our primary winding is feeding in this case, about 120 volts. Our little filament winding is pulling out about 3 volts. Now you could pull a lot more amps out of that, but they don't for this case because it's just feeding the filament. And then up here, we've got a ton of voltage, but only a tiny little bit of current because the wire is really tiny, but there's a lot of turns of it. The more turns you have, the more voltage you have on the secondary side. The more turns, the more voltage you're going to get out of it. But the trade-off is the more voltage you get, the less current you get because you're always going to be able to get the same amount of watts. Whatever watts you put in is going to be the maximum amount of watts you can get out minus some tiny losses. But we're working in physics land. This is education. So let's just assume an infinite frictionless plane and spherical cows. You do always have some kind of losses in a transformer. If the transformer is getting warm, if it's making sound, anything like that, you're losing a little bit of energy. At our power levels, it's negligible, so it's not something you really have to worry about. If you get a career in power generation and distribution, that's a thing those guys got to worry about. But here, we've got our input voltage at medium, 120 volts, our output voltage there at tiny, 3 volts, and then our output voltage here at high, like 2,000 volts. But while we get low voltage on this winding, we could get a lot of current. We could easily melt that winding if we wanted to. And here, we can get a lot of voltage, but we can't really get any kind of current out of it. MOTS, comparatively, have a high current output arc, but that's usually because when most people are playing with them, they're overdriving the hell out of them and they're 10 seconds away from melting down at any given moment. I'm going to be doing a video in the near future, it's the bicycle video, where we're really going to get into buck and boost and how that works with transformers. But for right now, that simple explanation will get you started as learning about more windings, more voltage, less windings, more current. Think of it like that. All right, so to wrap up, the last thing we're going to do with our brand new, to us, microwave oven transformer is we're going to remove the filament winding because you don't need that. You don't want that, and it can, if mishandled, cause you some problems. So on here, we can see there's a little piece of tape holding that. So I'm just going to cut that tape. I'm going to be careful not to nick any other parts of the transformer because I want to cut just that tape, and that should tear out. Now this is all encapsulated, coated, like this whole thing was probably just dipped in like a varnish. So everything's kind of sticky, but we're just gonna cut that apart And sometimes you can't actually get this all the way out, and if you can't, that's okay. But the idea is to just cut it back and clean it up as much as you can. As long as the ends of the wire are well clear of everything else, you're going to be okay. But you just want to make sure it's not going to touch anything. If you can remove the whole winding, just yank it out. But you want to make sure you don't damage anything in the process. So this is so I've got it trimmed off short. Now you ask the question, do I feel lucky? I don't know. I think I'll give it a shot. That's as cleaned up as I can get it. I separated out into 6 little short stubby bits of wire, and none of them make a full circuit. It's just 3 little pieces here and 3 little pieces there, and that's not going to get enough induced voltage to cause any problems or be any count. And I'm nervous that if I try taking it out any further, I'm just going to kill this mott, and I'd like to not kill this mott because we're going to do some cool things with it in some upcoming videos. So that's as good as I can get it cleaned up. But now we don't have the big red wire hanging off that wants to short out or arc out to something. So we're a lot better off there. You guys have fun. That's your detailed look at motts. I'm Chris Bowden, and as always, we'll see you next time.